we could almost say, oh, we've done it, right? You could say, okay, you taught us the standard model, why don't we just, forget about the rest and enjoy the next few months. You know what the standard model is. We derived the basic interactions. So as I said and I started, we have to, however, see what it means. What did we really achieve? We found out that if we were to gauge the weak, besides the electromagnetic interactions, we needed the gauge group to be SU2, which we call SU2L, while L here, to remind you that only left-handed fermions have weak interactions. Only left-handed fermions know SU2. So only left-handed fermions can be doublets under the SU2 group. And we said we need an extra U1 that we call hypercharge, which meant that the fundamental fermions, the left-handed one up and down, leptons and quarks, are doublets, which means, by the way, that TA is sigma A over 2. Okay. Right? We have an SU2 transformation. In SU2, U is e to the I. So this acts on everybody. I can have triplets. Maybe tomorrow someone tells me that there are triplets or there are quartets. By the way, gauge bosons are triplets. No problem. I just need to take an appropriate TA. Okay, on these fields, TA is Pauli matrix, right? Then we have the right-handed fields. They must exist because the photon couples both to left and right. So I can't not take them. And by the way, they are massive. Electron up and down quark. I don't take right-handed neutrino because nobody saw it. Okay, I will be punished for that. Okay, this is good. At least something failed in this beautiful, predictive, and extraordinarily successful theory. And neutrino will turn out to be massless. But anyway, this is how it started. We are looking at the minimal standard model. So here TA are 0, right? It's a singlet. U must be 1. And we said we can always find the appropriate hypercharges from the formula that relates the SU2 quantum numbers, the U1 quantum numbers, and the electromagnetic charge. We can, when needed, emphasize that this is electromagnetic charge. If I don't say anything, I mean electromagnetic. Okay, I may forget. In principle, there may be other charges when we talk about color. And everything came from our covariant derivative, right, which was d mu, minus I, the coupling constant G prime. I needed to introduce the relative strength of this coupling. It's called weak mixing angle. This was a covariant derivative, and we identified the physical fields. By the way, what we are doing, we want to unify electromagnetic with the rest, therefore we assume that there is a photon. I'm not proving that there is a massless gauge boson. At this point, anyway, they're all massless. Strictly speaking, there is no difference between any of these interactions. I'm hoping that something happens in the process, okay? But for the time being, you can say, why are you even changing the names of the fields? They are all equal, basically, okay? Because we know that we have to reproduce the real world. And we found out that we have interactions. There is a charge interactions. Let's put a plus sign, which is G over square root of 2. We found from this covariant derivative, W mu. We found also the that we could easily accommodate this. The electromagnetic one and the new neutral current with their overload strengths cos G over cosine theta W. Notice that, by the way, E here is G sine theta W. This is a fundamental relation. I could write everything as a function of E. I don't really have to introduce another constant because all I have to measure is one parameter theta W. So maybe it would have been even better not to introduce two couplings, but traditionally one did historically, so we'll keep it. If it was truly unified, you know, theta W would be 90 degrees, sine theta W would be 1, it would be equal to G, but that doesn't make any difference. I can take it into so there is E mu. Notice the analogy. It's sort of exactly the same time of interaction. The strength is a little different, okay? But the form basically is the same. Instead of one neutral generator, we have two now. We can write this in the universal form because the appropriate quantum numbers are read off by the quantum electron, by the charge. If you tell me here that this is an electron, I'm obviously summing over all the particles, right? Psi stands for all the particles in the all the matter, if you wish. This is what the universe is made of. Okay, there is nothing else. Okay, these funny other generations are just a product of our restlessness, so we have these funny machines in which we bombard the particles and produce this strange, funny junk. But these particles don't really exist, they decay. The universe, you and I, and everything we see is made of these particles. By the way, even neutrinos, I don't know if you know that. That cosmology sometimes, I don't like that, they often neglect to talk about that. I remember our peers, they would come and lecture in the school. And they would tell us, well, the standard model is great, this was before the Higgs. But how can you accept it before the Higgs is found? We all knew that the Higgs had to exist, and you will see why in a week or two, 3. We have this Big Bang model that we all accept, but it has one major prediction, as important as the Higgs in the standard model is, and that is that there must be neutrino C, right? You know that there is a photon C, discovered accidentally in 1966 when two guys were cleaning their antenna. There should be neutrinos in the universe. You heard of this? Paolo will teach you. And you can understand why it has not been detected. You know that there are photons. I'm sorry for these side remarks. I can't help them. I want you to see correlations, okay? I don't want you just to follow the formalism. We know that there are photons in the universe, right? It's a cold universe. The temperature of these guys is very low, bloody low. You know what the temperature is. Roughly 2.7 degrees Kelvin, right? There's actually neutrinos in the universe, which is also very cold, almost the same. They're supposed to be there, which tells you that the numbers should be more or less the same, right? The temperature tells you how many there are. When you go to very, very, very early days, when the universe was very hot, then the only scale was the temperature. So you can think of the number as the number density was given by the temperature. Okay. Why can't we find them? But by the way, the temperature corresponds to energy. You know what is this energy? The kinetic energy of these guys? In whatever units, in GeV, MeV, EV, whatever.
Minus 4 EV?
Sorry?
Minus 4 EV?
Minus?
4 EV?
No, much smaller. No, forget the number, just the order of magnitude.
Okay.
Yeah, the 4 is there. 10 to the minus 4. Sorry, you said why? No,
Okay.
okay, that's what you meant, sorry. You see how small the energy is. You know, it was hard enough to detect neutrinos from reactors which had MeV energy. You can imagine electron wall energy. Neutrino doesn't want to interact with anybody. So anyway, so this is why I stick to one generation. I will always do that. Whenever I want to understand the fundamentals of the theory, I will pretend that there is one generation. Then when I want to understand how they mix, I will pretend there are only two, because there will be simple analytic formulas. And I advise you to do that, and you just look at the 3 generation when it's really necessary, okay? Because it's a mess. So now we have a new interaction, and as we said, everything can be determined from 1 by 1 universal parameter, which is theta W. Therefore, I can look at any process, and it will only depend on theta W, agree. By the way, now some important comments. In some books you will read written like this. Okay, let me write here, the way I wrote it, and in some book it will be written like this, where L is the usual projector, right? What I derived is incorrect. It just came out from asking that there was a photon, so I should be right. But then the book says it's unlikely that books would be wrong, right? So can you help me to see why the 2 expressions are both correct? I'm helping you. Note that there is no chirality in the case of photon, okay? This is very important. And how do you know that there is no chirality? Because left and right fermions have the same charge. That's the same that's the same statement as the fact that electron and positron have opposite charges. Okay, to a great precision. Again, the precision is about 1 in 10 to the 20. Okay, the universality of charge. Well, the answer is here. T3 picks up the double. I don't have to put the left, because if I take the right-handed fermion, T3 would be 0. If I take the left-handed fermion, T3 would be what it is, but then automatically L will give me, because when L acts on psi L, gives me psi L, right? And when L acts on psi R, gives me 0. But so does T3. When T3 acts on psi L, gives me psi L. Sorry, the eigenvalue. And when that's on psi R, gives me 0. So T3 is selecting left-handed fermion. So this is how you should read this formula.
So we could in principle wrote the generators in the bigger SU2 times U1 group, like a 3 by 3 matrices. And then it will be...
Yeah, but they will be block diagonal. That's what it is, right? Then if I do that, imagine, then I should also write the Lorentz generator. So it's all this block. Since they are block separated, I don't do that.
But I mean, there is also, there could be the right-handed representation, which turned out to be trivial. So
it could have been, but
like
it could have been that would have been another world, right? Sure.
We put it as a block, another block, and we could see that the representations chosen by the Pauli matrices is the left-handed one. I mean, it's just the notation, but
I'm not sure what you are. Are you telling me that the world could have been different, or that I could have used different conventions?
Yes, it's all about the conventions, because like what you say is, I think, what I understand is sigma matrices, you just act from the left-handed piece, not right-handed.
Well, I say it when I write this. I'm writing this for you. I don't have to do that. Once I write the representation content, then you should be... if the content is there, sorry, content. If the content is there, then you can read off the... I don't have to do that, and I will never do that again. This is just in the beginning of the course. So if I write the representation, write phi 1, phi 2, phi 3, then I don't want to tell you what the generators are. You read it off, right? That's a group theory. You've learned group theory to the level that is... Narayan taught group theory, right? That's another level of group theory, Narayan and me. My group theory is here, you know, right? You can imagine the group theory need to do the kind of research that he does, okay? So obviously when he teaches you, he's going to teach you more sophisticated. He may have taught you Dinkin diagrams. I wouldn't have taught you that. Anyway, maybe I should have, but I wouldn't have. Right, so it's clear. I know I'm sort of giving you a hand at the beginning, but then I want you to really, you know, knowing group theories, that comes later. I'm often worried, to tell you honestly, that I sometimes see, you know, students doing these great things with group theory, but not really understanding SU2. That's worried. You have to grasp SU2 completely, and that's what this course is about. Knowing SU2. That's all. I will cite field theory. You won't learn field theory here. Okay. So, for example, if I tell you how does the Z boson interact with neutrino, right? You will have to do that in the homework, okay? I take a neutrino. It's very easy for me because neutrino is left-handed only. I don't have two neutrinos. So you see how it would look. T3 would be, what's T3? Should be a little faster. 1/2. And then it is left-handed. So it would act like this. You know, I have a question, is parity violated in some with neutrino, is parity with the electron? I won't answer it here, but you can think about that. This will be the neutrino. If I ask you, well, how does the electron interact with the Z boson, then you can tell me, well, do you think electron, okay, I can add them up, but maybe we should do EL first and ER because they interact differently. It's better to, before you are, you know, clear about things. So how would EL interact? I'm not writing gamma mu, okay? There is always Lorentz. T3 is minus a half grade. It is left-handed, I said. The charge is -1, so this will become +1. ER here 0 plus sine squared theta level. This piece is of course universal when it comes to the charge. It's just like the photon. If there was no T3, I would have had another photon.
It's plus or minus the sign.
Where?
The sign squared.
I think
Plus.
this time. I don't guarantee.
It's not.
Basically, every time that you ask me, I was wrong, but this is correct.
Are these so-called charges according to the Z boson?
This is electromagnetic charge. The usual charge.
No, the whole term that we write the results of is the hypercharge.
Hypercharge. I forgot about hypercharge. I don't want to even think about hypercharge. Hypercharge, well, you can express it as a function of hypercharge, but why would you do that? You and I don't know what the hypercharge is. Well, you know, you said, oh, I've learned. Imagine when you go to very high energies, then, you know, symmetry stops really being broken at very high energies. Particles are basically massless, and then you can say every quantum number is as good as any other. You can live with T3 and hypercharge. I just don't want us to learn something new. Charges you know. If you didn't know, I would have then, of course, worked with hypercharge. But you know charges, QED came before. And T3 you can read off immediately, okay? You don't have to remember it. All you have to remember the content of your matter field. So, so for example, you can say the interaction of the electron will be minus 1/2 1 plus gamma 5 over 2. And here, oh, this was left and this was right. If I say left and right, then I have to put a projector. Because it wouldn't interact only with the left-handed guy, which is hidden here. Which of course tells me that if I have complete fermions, then left and right will sum. the piece which is universal. So you would have plus sine squared theta W. Left plus right is 1, which I can read off here. It tells me now I can look at the electron, and I can look here. The electron, I don't have to separate in left and right. I can, with some experience, think immediately of the electron. Okay, it has T3 times L. I read off automatically because only left-handed electron lives in a doublet. And the other pieces. Notice if you take sine squared W to be a quarter, that you get minus gamma 5 over 4. So I told you here it may be convenient to write in the approximation it's a quarter, because I'm going to ask you is parity broken or not. It's easier to see in this limit. And so on and so forth. So now we could write down, let's say, one more upward. Okay, how would the upward look like? T3 half L, only left-handed quark is a doublet, minus 2/3 sine squared theta W. Well, let's write down quark, so everything is here. It will be minus 1/2 L plus 1/3 sine squared theta W. Okay, a little care must be done only because of the T3 piece. The rest is universal. The Q term is just like the photon. You don't have ever to think about it. And I think it was Mehmet asking me, of course. Now it tells you that electromagnetic interactions have to be corrected by the presence of Z. It also couples to charge. How much depends how heavy this guy is. If the mass of Z is infinitely large, then you would basically not have it, right? The heavier the particle, the more decoupled we say, the less present it is.
You would have first this expression for the whole up and down quarks, like right and left, right?
I could have written right and left.
I mean,
I didn't want to do that. I summed immediately. This is the whole thing.
Yes, but in the second term I agree, but the first term, because maybe we will have another doublet, so...
Which another doublet? There is.
If you are and DR, we will have a doublet from them or a doublet.
In another world,
Okay, no. Okay.
in another interaction, actually maybe, okay, well,
Yeah, that's right.
that's what I'm told. That's what Madame Wu told me already in 1956. It was around Christmas when they announced this incredible thing, that parity seems to be maximal growth.
Yes, sir.
By the way, you checked it with the W decay. You got 1 minus cosine theta or 1 plus cosine theta, depending how we wrote it. I'll send you the picture if you wish. The beautiful discovery of the W boson, you know, the 1983, the Ruby et al. Experiment, and you will see that it just fits beautifully with 1 minus cosine theta. That's why I forgot to do that. I wanted you to yourself see how well it fits with maximum parity violation. It's a strange world. To this day it bugs me. Somehow it shouldn't be like this, but it is. Okay, the thing, of course, at this point, these are more words still, because you may ask me, well, what is the impact of the Z boson? How do you know what the mass is? You have no idea. You have some hint. Remember we said that GF over square root of 2 was E squared over 8 MW sine theta W squared. Remember we derived this at low energies from the exchange of the W boson just by taking the usual massive propagator that you derive. So I don't know what MW is, but I know that MW sine theta W is 80 GeV, 40 GeV, sorry. Roughly. So when this is a half, I get famous ATGV. This is the mass of the W boson. And you can say, well, do the experiments immediately and measure theta W. You can tell me, well, measure theta W. If you measure theta W, you can then immediately find MW. But that means you have to do the experiments of neutral currents. Of course, if you do that, you will also measure the Z boson mass, because, so I just want to tell you it was simultaneous. Knowing MW would immediately tell you what MZ is, because, where should we do that? Let me not erase the interactions. This you can reproduce. Because you would look at some scattering. I don't know what we wanted. We would look at the electron scattered on the up quark, say, some physical process with a Z boson. It's not so important even what I put. The thing is that I will have the interaction, we will be G over cosine theta W squared. And I could write this. Actually, I could have written G is E over sine theta W. So this is also equal E over sine theta W cosine theta W. Right. The strength. So I could write like this, just to emphasize the same thing. I will get E squared over sine squared theta W cosine squared theta W. Then I will get 1 over mz squared from the propagator. Remember, only 1 over at low energies, Q is 0. So the propagator is 1 over mz squared. Somehow I think in the first problem, I look in the first problem. It seems to me very few of you answered the question that you were asked. Tell us the high energy behavior of the propagator. I wanted to know, does it vanish? Is it 1 over Q squared? I don't think you answered it. And I think it was, Vishal, it was equally lenient with all of you. He sort of, okay, it doesn't matter, it's relative, okay? This is what is a fundamental question, remember. For me to know how the theory behaves at high energies, I have to know how the propagator behaves. It must vanish. This one doesn't. I'll come back to that. And then there will be this thing that I put there, right, of the electron interaction, these terms. So notice, if I am, and they depend on theta W, I don't even want to write that, I've just erased it. Whatever expression was there. If I'm able to measure theta W, I will also measure mz, because I will measure this process. So the things were basically simultaneous. In the early 70s, when people started to do these experiments, they of course determined both MW and mz by determining theta W.
Is there a reason that we find a different mass for Z boson?
I would say the other way around. If I see two things which are equal, then I ask myself why they are equal. If you guys were exactly the same height, you know, and the same mass, then I would ask, why is it that you two guys have the... But you don't ask that. You don't ask me why your mass is different in height from Nicholas's, I'm sure. So normally, if there is nothing deep, if there are no symmetries, we expect the masses to be different. Turns out, actually, that they are remarkably similar, and that's surprising. And you will see that there is a surprising thing in the Sander model that makes W and Z masses basically the same in the first approximation. I'll be clear. So we'll have to come back to that. The determination of MW and Z, we'll discuss that. The point is that at this stage, at this theory that Gleshow wrote in 1961, he couldn't make any predictions. Right? He didn't know, if you wish, the relation between W and Z masses. Actually, when he writes his theory, he wants to have a gauge invariant extension of the QED. Therefore, all the particles should be massless. They are not. So Glescher says, okay, I'll give them a mass. You tell me how much they're heavy, I'll add the term to the Lagrangian with that mass, okay. So you may ask him, then why the rule? Are you writing a symmetric theory and then you are breaking by hand? Right, why does he care about gauge invariance if he's willing to break it? And he must break it, because Z is not massless, W is not massless. He knows that. He knows that they are quite heavy, nobody observed them at that time. You know, he knows it somewhere in the GeVs, pretty big. And Glescher was not completely stupid. He's not completely stupid. The point is, that there he must hope. Normally I would say, look, the thing that matters really are interactions. Because when I worry, and I've tried to sort of hint at that, I couldn't, you will learn that in your field theory course. When I worry whether the theory is well behaved, well, I have to worry what happens at high energies. I have my Lagrangian, then I want to use it at high energies. I want to be able to integrate all the momenta. And therefore, I am interested in E basically going to infinity. By this I mean E much bigger than the scale in question, whatever. If I'm looking at proton and neutron, I mean the energy which is so big that I can neglect the masses. And then you reason, well, at those energies, masses are irrelevant. Obviously. The bigger the energy, the more kinetic energy you have, the less is your potential energy due to the mass, the static part. That's a convincing argument. Well, he knew that there was a subtlety. It's true of all the particles in the world, except for gauge bosons. We found this crazy thing about gauge boson when we wrote the propagator. I want you to do homework about the Z boson so that I can discuss it more deeply, okay? This is why I want to stop here. I don't want to tell you some things that may be relevant for the homework. So we said that the propagator for a massive field it doesn't even matter the coefficient, was proportional to this. I will write this so many times, you know, it will be ad nauseam, you're gonna hate it, okay? Just to emphasize that there is something crazy about the massive gauge fields. It's very different, for example, from a fermion propagator. Or a scalar propagator. All the propagators, the scalar propagator will have this piece, right? So they vanish at infinity. Fermion linearly, 1 over energy, scalar 1 square, but this one unfortunately doesn't vanish at all, right? Because there is this piece, when Q goes to infinity, so this goes as 1 over ma square when Q goes to infinity. So Glescher knew that there could be a problem, but he says maybe one day we'll understand, and it was true. Some years later already the answer started to creep in, okay? We may be able to understand how to deal with this, okay, because there's got to be a way. Okay, he had a profound insight. He said, I'll still write the theory, because I have to do something crazy. I have to pretend that the symmetry is not broken, and then I have to tell you that it's broken when you tell me that particles are massive. And of course, he had no problem giving fermions a mass. Just by hand, he says, okay, electron is massive. Then you tell him breaks gauge invariance. Okay, he says, but go to high energies, you will recover gauge invariance. And that's where you need it, because you want to study your renormalizability, okay? Your high energy behavior. This is where you want to see whether your amplitudes are finite or not. And this is why we have proceed, but at this point we are blocked. And it's not surprising that for another 10 years people will be blocked. Those that thought about it, like Weinberg, who spent years on that. You should see it was last year or a couple of years ago when Weinberg was it? Maybe 2 years ago when he gave a lecture, it was for ICTP, you know, he used to be a good friend of ICTP. They were friends with Salam and they collaborate together. And he gave this talk, but you can find a video of the talk. And I've heard him say that on some other occasion, that to this day he says every time he does something stupid at home, you know, when he goofs at home, his wife tells him, you couldn't renormalize your own theory, you know, you moron. Okay, it's a thing that stayed with him all his life. And the reason is that the Weinberg would work with this propagator, and this is manifestly badly behaved. Okay, any loop with this propagator, remember, I showed you will diverge because the integrand will not vanish. And this is why you and I have to cure that. Okay, I want you to somehow appreciate that it was theory that preceded experiment. This is how I want you to be taught. I would have started with that. After all, there is a Higgs boson, I can just start with the Higgs mechanism and go on. I want you to see how we were pushed into it. This is remarkable. We have to find a way of rewriting this propagator. That's all we have to do. It will turn out to be a profound issue, but basically you and I have to find a way to make this propagator be 1 over q squared, like photon.
Is it the only way to make it renormalizable and with 1 over q behavior? Is it the
well, the only way we know is precisely the gauge symmetry. It may be there. If it's not there, it must be spontaneously broken. That much has been proven. You cannot break gauge symmetries explicitly the way I'm doing it here. You cannot do what Proca did. They won't work. And you will see that, by the way, you won't be able, it's obviously nothing to do with this course, but I'll show you, for example, in some of the physical decays, how the spontaneous breaking cures the problem of the limit. There are two limits here that you can see are bad. One limit is q going to infinity, right? The other limit, equally interesting, is mass going to 0. Because you would say, oh, why can't I take the mass going to 0 limit? That's sort of, look, I can take here mass going to 0 limit. Just let me assume that the mass is much smaller than the momentum. That's similar to making momentum very large. So you say, okay, forget your large q square. I don't want to study normalizability. I'm lazy, I just want to do physics with W bosons. So I will look at some decays. And I will take a very energetic particle decaying into a W boson. Or just imagine that I'm at the small end. Notice that this diverges also in the limit MA going to 0. There is a genuine problem here. I want to make big fuss about it. You know, we're going to create a drama so that you and I really understand that we have to study new material. Okay, I want you to appreciate that. I'd like you to be reluctant to be taught new things. I know you grew up like that everybody tells you you should learn this and that. And maybe some of you have that. Be careful. Try to learn as little as possible so that you can learn it deeply. And that you know that you must learn it in order to be a physicist and to be able to do research and to maybe discover or be a part of a discovery. I want us to see that we really have to learn something new, start from scratch. Because I don't know how to proceed here. And I hate now to make you learn other things for weeks now, which have nothing to do with the physics of the standard model at first glance. And what I have to do, I'll make an educated guess. It's easy now from my perspective. It turned out that even before they were worried about this in the 60s, Stuckelberg, a Swiss physicist, a genius, have actually thought about it and offered a solution, but nobody paid attention. There was recently a conference of the 50 years of the Standard Model together with Pascos, and Weinberg gave a talk. And I'm asking whether he didn't know Stuckelberg, or he simply knew and ignored it. The answer was, can you really understand his paper? So as if he knew about that. He wasn't very clear. Okay, I was very curious, why is it that this was omitted? Okay, this name will pop up from time to time. What he thought is extraordinary, simple and profound. He says, what do you do with a photon? In order to understand what we have to do, take the photon. It has only 2 degrees of freedom. Right? These are the transverse components. But you and I pretend, but we work with E equal 4. We like to do that because that way we have Lorentz covariant expression. What we also have, we have gauge invariance then, gauge covariance. If we want to work with 4 degrees of freedom, we will recover that there must be, because there are redundant degrees of freedom, there must be a redundancy in question. The theories, plus or minus, depends how I call it. The field itself cannot be physical because there should be a freedom in changing the 2 of its components. Okay. So he said, look, in the case of a massive guy, so this is the photon, in the case of Broca, when MA is equal to 0, you have actually 3 degrees of freedom, spin 1. But you work with 4 degrees of freedom for the same reason, to have Lorentz covariance. Then you lose gauge invariance. You don't have extra 2 degrees of freedom. So he said you should stick in another unphysical degree of freedom. Maybe then you can work. What he said, okay, this is, I don't want you to understand this, just relax and watch this, okay? We will come to this in a systematic manner. He says when you write this term, MA squared, A mu, your problem was that this breaks this so-called gauge invariance, and then you don't have a well-behaved propagator, okay? He says, why don't you work with this? Introduce another degree of freedom, call it G. There is no that degree of freedom, just the way I do with the photon. I've introduced an extra degree of freedom, not just 3, I had 4 degrees of freedom. They don't exist, I've introduced them. Only you didn't pay any attention that you introduced them. They were introduced from the beginning. So you never even thought about it. Okay, this is the difference between you and me and a genius, okay? He thinks how you got there. So he says, look, do the same thing. This, of course, will not be physical. This will be like longitudinal photon, you're never going to produce it. By the way, I have to put 1 over m for dimensional reasons. There is a derivative here. And G and A should have the same dimensions. So if I put a derivative here, I have to put 1 over. I told you, just relax. Try to sort of watch this, enjoy it. Okay, please. We will now do a couple of weeks of serious study to get there. But I want you to appreciate where I want to take you. This is easily gauge invariant. This is invariant as long as G goes into G plus MA alpha. You agree? I recovered gauge invariance. And then he showed that the propagator will look okay. So the solution was actually there. He actually basically arrived at Feynman rules, but he wouldn't draw them. He was a baron, he says, a gentleman would not draw, okay? Anyway, he was considered strange. He had serious problem. He was taken to madhouses, as you call mental asylums. It's a tragic story of a genius that you can read about him. every continuously as the time goes on, people are discovering important works of his. So, the trick is, you and I need extra degrees of freedom. They will not come out of nothing magically. We'll need them so that we will be at the end just able to rewrite our operator. But that will change modern physics completely, okay? Well, forget it. This is not, it couldn't be heavy. So what I have to teach you, I have to teach you a way, as Nambu called, of having a symmetry and not having a symmetry at the same time. With C and Yang tells me, well, that's impossible. Symmetry is either there or it's not there. Where apparently it's not true, okay? And that's spontaneous symmetry break. And it's not a big deal. These examples exist. In real life, Salam used to like, remember this round table thing where the glasses are on left and right, and once the glass is picked up, the symmetry is broken. So we will do spontaneous symmetry break. What I found really amazing somehow, I'm in awe of this. I would have doubts, but then somehow I would be more and more convincing that this what will follow, which will tell us what the origin of particle masses is, was developed only so that you and I can be able to do calculations. There was no other reasons. There was no physical problem. There was no issue to discuss with this. It's not like a problem with black body radiation or something you have to modify your physics. Okay, it often happens. This is so just that we can do this naive perturbative calculation. That's sort of amazing, you know, that nature is like that. So in order to show it, I'm going to take the simplest example of the simplest field, the real scalar field, and I take the simplest symmetry, just a discrete symmetry, okay? So we'll start with discrete. The Lagrangian, as you know, if I have a real scalar field, so I have a field which is real, is the Klein Gordon. D mu phi squared minus 1/2. Well, why not I write better? Minus a potential. Let me ask for a discrete symmetry, phi going to minus phi. Now, why do I write like this? What should I take for potential? I'm going to take the simplest possible interaction, which is discrete. But it has to be an interaction, therefore I have a mass term and I have the interaction. And let's take the simplest one, which will be that's phi to the fourth. I cannot write phi cubed, that will be making it simpler, but I can't write it because I'm asking for a symmetry phi going to 1. So this is my potential. By the way, you will learn that this is the most general potential I can write if the theory is to be renormalizable. This is beautiful, okay? At 3 level, at the classical level, this is what you have to write. Of course, the loops may generate more complicated interactions, okay? So I'm actually taking the most general scalar field theory that possesses a symmetry phi going to minus phi. These are just words at this point. I'm also taking the simplest. So how does the potential look like? It looks like this. Well, first. Lambda. What do we know about lambda? It's dimensionless. What else do we know? So lambda is dimensionless, okay. Can it be complex? No, because this is a real field, the potential must be real. Okay, so the first thing you know that lambda is real. What about the sign?
Positive.
Must be positive. Because otherwise there will be no minimum, right? You don't want to live on the abyss. You will fall down. So this is very important. Lambda must be positive. And once you know that lambda is positive, that determines the high field behavior. This is like a parabole, only steeper. So it's just going to grow steeper. Where I have implicitly assumed that m square is positive. Why? Because from here I can derive the equation when lambda is 0. Right? I get a Klein-Gordon equation. You've done this more than once, I'm sure. You probably are studying it, or you've finished with the scalar field. With Safes, you've done the field theory of the scalar field, right? And that tells me on mass shell, when I go in the momentum space, I will get that E square is P square plus M square, right? This M is actually mass of the particle. And therefore M square has to be positive, otherwise I will get the tachyon. So it seems that this is a situation, and this is what people would take it for granted for a long time. Everybody thought this is the way it has to be. It seemed kind of obvious. Symmetry, phi going to minus phi, notice I should live around the ground state, you and I should live here. Okay, when we study our particle physics system, we study the behavior, we do perturbation theory, we live near the ground state, okay? We didn't say that explicitly, but that's what we do for a living. We just look at the small excitations around the ground state. And the ground state is completely symmetric, left and right. Therefore, this is a situation that you've used always, okay? You have always assumed that the value of the photon field in the ground state is 0. You assume that. And this is a typical situation, the value here. Okay, let's introduce a fancy language, a vacuum manifold. Is a set of all points phi 0 so that V is at minimum. So that V is minimum. What is the vacuum manifold? Okay, forgive me for this fancy language. It's interesting when you have complicated topologies. You can imagine, and you will appreciate these words, this notation, this language. What is a set of the points? What is a vacuum manifold? It's just one point. Phi 0 is 0. Notice that my discrete symmetry phi 0, when it acts on phi 0, it leaves it invariant. Okay. Discrete symmetry takes phi 0 into minus phi 0, right? But phi 0 is 0. So D acting of phi 0 gives me phi 0. This is a situation we describe by the vacuum being invariant. Okay, I'm slowly telling you what you knew, but never paid too much attention in field theory. It's not enough to know your Hamiltonian Lagrangian equations. You need to know the ground state. In quantum mechanics, you worry that a lot. Only when you know the ground state, you can start doing physics. Okay. What we are trying to do today is determine ground states of various examples as we go along. And here is an example of a symmetric theory with a symmetric ground state. I have to find, actually, what I have to do, I've told you basically, I have to break the symmetry. So I failed, it seems. If I cannot do it here, I will not be able to do it in any more complicated example, because here, in this trivial example, everything is here. If you understand what I'm saying today, you will understand the rest of the symmetry breaking. There's just going to be some groups here. But the potentials, they look exactly the same. The physics, the mass will be basically the same. I have made an assumption here, which seemed obvious. I made two assumptions. Lambda equals 0 and m squared positive. And it seemed necessary. Lambda equals 0, this just means the potential bounded from below exists a minimum. And I probably shouldn't touch this, right? But I cannot touch this, there will be no minimum. So let me try to change this. In other words, let's do it better maybe. Let's write like this, and let's write this was plus m squared. Example. Give me nothing. I have a symmetric theory with a symmetric ground state. So now let's take the example number 2, minus m squared. You're saying, but look, that's a tachyon, and there can be no tachyons. Well, I say, please wait. Let's see if it's really a tachyon. Okay. There is an assumption in concluding that this describes my particle, okay? And you will see why. What happens if I take, so in other words, the potential now looks, let me write it once again, minus 1/2 m squared phi squared plus lambda over 4 phi to the 4th. How does it look like, this potential? Let me draw it, and then let me not do it in the student way, okay? The student way, you will find the extrema, you will plot it, okay? But let's just think. What happens at 0? Potential is 0 here. Is it a minimum or a maximum? Local max? No, it's a local max. Well, I mean, why? Because d square v over d phi squared at 0 is minus m squared, and this is negative. So that means it's going down here. Or agree? What happens when phi is very large? Well, lambda wins, I said. So it has to go up. So that means it will have to go like this. All I have to determine, and of course the potential is symmetric. All I have to determine what is this point. I'm going to call this point V and minus V. These are the points of the local minima. Well, global minima in this case. In general, maybe local minima. You know, this is the potential that I took at the so-called 3 level. It may, if I go very far, the further away I go, the less maybe I trust what I conclude. Okay. What? Sorry. The way I drew it, pretending that this is my complete potential, these are actually global minima. Can you guess what V is? dV over d phi at V0. So you get that V square is m square over lambda. You'll get it immediately. There are, of course, 2 such minima. I had a discrete symmetry, so there had to be 2 minima. So this is the theory I started with. It's a symmetric theory because I started with a symmetric Lagrangian, which we have a symmetric Hamiltonian, and of course the minima must be symmetric. What is the vacuum manifold now? Is phi 0 square equal V square, right? This is the set of points that give me, this is the definition of the vacuum manifold when V of phi is the minimum. So this is plus or minus V Notice an interesting thing. D acting on phi 0 gives me minus phi 0. The symmetry is not invariant anymore. The vacuum itself breaks the symmetry. This is the first example. This is one vacuum here. It's not symmetric. A vacuum is not symmetric. When I perform a transformation, I go from one vacuum to another. But the vacuum itself breaks the symmetry. In other words, if we have to live here, if I look at the perturbation theory around the small minimum, around the minimum, if I look at the small excitation, if I want to know what happens to my quantum fields near the ground state, okay, then the symmetry is broken. In other words, if I live in the whole space, the symmetry is there. But if I have, imagine, there is a small ball put here and the ball is heavy and I can't easily take it up, then of course the symmetry is broken. The ball can be anywhere. You and I can live here, or we can live here, of course. But once we choose where to live, the symmetry is broken. Vacuum. Vacuum is just a name for the ground state, okay? Vacuum breaks my symmetry D. This is an example of spontaneous symmetry break. Everything is symmetric, but if I live in one of these two states, symmetry will be broken. Yes, of course, you may say, but it's trivial because your theory doesn't make sense. Your m square is negative, you have a tachyon. However, and here's the catch. If I say that you and I have to live here, and by living somewhere, what we study are the small excitations around the ground state, that means phi is not a good field. I was wrong when I gave it, in my notation to start with. It was very convenient because with the name phi I have a completely symmetric theory. But actually, phi my field phi, what I need, what I'm after, I'm interested in a field that lives near my ground state and describe this quantum theory I'm after. These will be small excitations around the minimum. I could have decided to live here. Okay, you should convince yourself, we will see physical quantities cannot depend on whether I choose to live here or here. There is a complete symmetry. But what I'm saying that H is a physical field, not phi. I should compute the mass of H.
So H would obey the right energy relation.
Sorry?
So the physical field H would satisfy the normal dispersion relation.
Well, we should check. Very good. It should, hopefully. It seems that it should, right? Because now I live around the minimum, so the excitation, probably the second derivative should be positive, okay? But let's check it. Let's rewrite this. I can erase this left-hand side. This is not what I'm after. This particular portion of the parameter space, after all, I don't know. I'm studying the parameter space. And in this case, let's rewrite the potential. V is minus a half m squared V plus h squared plus lambda over 4 V plus h to the 4th, which is minus 1/2 m squared V squared plus lambda over 4 V to the 4th. I'm splitting the minus m squared VH plus lambda V cube H. Look what I'm doing. First I write the constant piece. This is some constant. I don't care about constants, right? Physics does not depend on the constants as it could be. That's the first thing we are taught. We only measure the energy relative to the ground state, right? Nobody can know what is the energy of the ground state. This is almost true. There is one interaction that knows about the energy of the ground state. It's called gravity. Gravity knows about everything. If Einstein is right, and everything tells us that he is right, after all, there are finally gravitational waves that were predicted a year after the theory itself, then even the ground state energy would matter, okay? And you will learn that in your cosmology class, how it matters. I don't care, it doesn't matter, because the gravity doesn't matter in weak interactions or strong interactions or whatever I do today. So I don't have to worry about this. So I will be very cavalier with this constant. By the way, the constant of the potential is called the cosmological constant. It has to do with the behavior of our galaxies. Okay, just words at this point, you will learn about it. For you and me, this is irrelevant. I can even set it to 0, you agree? Then I have a constant piece. Notice that this is 0 by the equation, by the extremum condition. V square is m square over lambda. You agree? So this is 0. What about quadratic piece? I have h squared minus 1/2 m squared plus, what do I get here? When I expand, I have v to the 4th, I have 4v cube h. Okay, let me write this. This is v to the 4th plus 4v cube h plus 6v square h squared plus 4vh cubed plus h to the 4th. You agree? So I will have 6 over 4 is 3, plus 3 over 2v squared lambda. Then there is h cubed piece. Well, this is what Mehmet asked me, I guess. He says the dispersion relation, presumably, I could stop here for a second, right? Dispersion relation here, notice this is going to be positive. M square is lambda v squared. This here, let's write down immediately. It's 2. No, this is just 1 minus 1/2 plus 3/2 is just v squared lambda. Plus h cubed. What about h cubed? There will be lambda times v plus lambda over 4 h to the 4th. You agree? Let me stare at it. Yeah, I think it's correct. Tell me if it's all clear. So there is a constant c plus 1/2 mh square h square plus lambda vh cubed plus lambda over 4 h to the 4th. Mh square, it's 2 lambda v square.
But we also lose the discrete symmetry in the both in the phi and h field. It's not symmetric anymore.
It's not symmetric anymore. We lost the symmetry. So you see, this is why Coleman liked the name hidden symmetry. He says there is of course a symmetry. Just use the notation of phi. You can use any notation you wish. You can use any variables you want. There is there is some review by Weinberg, I remember recently. Weinberg has a great sense of dry humor. He has some rules, you know. He has rule number, a golden rule number, whatever, 3. You see, it's all about choosing the right variables when you do physics. You want to do a spherically symmetric problem, you use spherical coordinates. Otherwise, he says, make sure you choose the right variables. Otherwise, you may live to regret it, he says. It's like an advice. Now, he used for years the wrong variables, okay? It may be as important as physical insight or mathematical wizardry. The sense of choosing the right variable. It's a crucial thing. And here, you see, you don't know what to choose. This is not trivial, okay? This is the work of Nambu and Goldstone. Goldstone, we generalize ideas of Nambu to prove what we call the Goldstone theorem that will eventually emerge. It all becomes more interesting when we do continuous symmetries, okay? Discrete case is a bit trivial. But notice that what we are proving out that there is something that I will call Higgs field in general. Already in this example, the guy that lives near the vacuum, we call this value V vacuum expectation value. Vacuum expectation value.
Which is different than 0.
Vev here is non-zero, V is non-zero, the vacuum expectation value. What actually, I'm studying a classical potential. I will have to show that the classical potential vacuum expectation value, the ground state number that I called V, corresponds to the actually value of the physical quantum field, right? This V is actually something like this. The value of the field in the ground state, which I call the vacuum, okay? I'm not going to do that. I'm just going to quote this. Instead of looking at the whole complete quantum theory, I can actually look at the classical potential. And what I found out, this can be proven rigorous. And I'm pretty sure that Saif will arrive somewhere there to show you this. We are learning that the field that has a vacuum expectation value, that lives with the vacuum expectation value, it will be called in a gauge case Higgs field, but the thing is here already. This was noticed by Goldstone, and I'm amazed how they miss him, okay? The Nobel Prize was given to Higgs and Angler, and it's not clear what they gave the prize for, because the Higgs mechanism was noticed by a number of people, the mechanism itself. The Angler and Brown paper did not have the Higgs boson. Higgs had the Higgs boson, I'll talk about that. But the Higgs boson was predicted before by Goldstone when he studied continuous symmetries, okay. It's already in this example, and it tells you the following, that when there is a spontaneous symmetry breaking, there is one physical parameter. This is the Vev. It has a dimension of mass, and all the masses must be proportional to that Vev. Which was this parameter M here. Notice that this parameter M was not the mass. It had nothing to do with the mass. I was wrong. In this portion of the space, okay, it's related to the mass, but it's not the mass. There are factors between them, okay? So the crucial parameter, and the way to emphasize that, and I will be doing that in the future, I'm going to write this potential. So obviously I'm going to choose the minus sign. I can forget this is not true. Phi is not the physical field. I can write this potential in a more elegant manner. Phi square minus V square, everything square. Do you notice that this is the same potential as before? M square will be here. That means that I added a constant here, which is lambda over 4 V to the 4. Okay, let's add this constant equal lambda over 4 V to the 4. Okay, it's true that gravity knows about the constant. You will be learning a lot about that, but you and I don't have to worry. By the way, it turns out that the constant is basically 0. There was a prejudice. Poor Einstein was not sure whether to put the cosmological constant or not. You learn Einstein equations. And you know that you can put a cosmological constant there, right? And Einstein was saying one day, maybe I should put it, I shouldn't put it. He didn't know that it has to do with the value of the fields in the ground state, okay? This was before his time. This will come after his time, sorry. Before our time. there was a strong prejudice that it should be 0 because the world is, people have, I don't know why. People end up thinking that small numbers should be 0. It's amazing how strong this prejudice is. When I started out, neutrino was supposed to be massless. It was a small number, so 0 is much nicer than. I'm glad I didn't subscribe to that. M squared is simply 2 lambda v squared. And it's better to write this way to emphasize that there is no mass term yet. You have to identify. Don't think of the mass term. First find your physical field. The original field may not be the physical field. You don't know, okay? And you can sort of guess. Whenever the sign is minus, you will see that something funny is going on. Normally there should be a plus sign in order not to be tachyonic, okay? This is called the valve, you see, because why is this notation useful? Because you can immediately read off what is M0, right? M0 is set of all points so that V is 0. It's faster to find the minimum this way when you write it, okay? And this is plus or minus V. There are 2 points. It's a discrete set that the symmetry D takes from one another. As Mehmet noticed, if I use the phi variable, the world is completely symmetric. And so you see, since physics should not depend on which variables I use, I have to learn. The same way I could learn, for example, you work with a photon which has 4 components. But someone says, no, I want to identify 2 physical components, I will work with that guy. You should get the same result. So if you decide to work with phi, or I work with h, we should get the same result in the end. We have to know, of course, to identify the physical situation, but the results should not depend on what variables we use. The advantage of this situation is obvious. I can read off physics immediately. There is one real scalar field, and it's not a tachyon, it has a mass 2 lambda v squared. However, I have no symmetry. And if it was a gauge symmetry, then that would be a problem because I need a gauge symmetry, okay? So the advantage of this notation is it's not physical. So this, we often call this a unitary physical gauge, a physical picture gauge. Imagine basically a gauge is, okay, this is a discrete symmetry. And here we call it, well, it will be a funny name. It will be a renormalizable gauge. It will be a gauge in which you do calculations. You need symmetry to be able to compute. Remember what I told you. So you and I have to learn that. And this will be the crux of the course. To somehow be able to go from one to another. I will be reading physics from here, but I will be often using this Lagrangian to do calculations. Carefully. Let's pause for questions. And I can rest my knee. My knee is still bugging me. So let me just write more, the same thing more neatly. V of I. I take. And this is the Boltzmann potential I can take with this discrete symmetry. And of course lambda must be positive. So it's better to stop here and leave this for Friday. But let me see if you can guess what I'm going to do next. How I'm going to do it. This was a discrete symmetry. I will take some continuous symmetry. See, I'm interested finally in a gauge symmetry, but I'll do it step by step. So I'll take phi going into e to the I alpha phi. Let's take alpha constant first. Can this be real field? No, it must be complex, obviously. So how will the Lagrangian look like? It will look d mu phi star minus v of phi. How will v of phi look like? I stop here. Let's just, you see that once you understood this example, we'll do everything else will be exactly the same. It's embarrassingly simple, the rest. The mathematics will be basically trivial. Reading of physics may not be so trivial, but mathematics will be trivial. Well, now it will be the absolute value square, because it's complex. So this potential will be lambda over 4 phi square minus v square, everything square. And you will again get this Higgs field, okay. This will be called Nambu-Goldstone picture that will be emerging, okay. The potential really was studied more carefully by Goldstone.
So,
I stop here.
okay, we're living in the vacuum, in the ground state, let's say this side, and we just see the physical situation only like around this one. So is the situation here that we introduce the new, let's say, I don't know, but the new configuration also, and
in a sense,
the change of the coordinate, just to be able to do calculations in 30.
No, here what we are doing is not to be able to do calculations. Oh, I can calculate any which way I want. Here is I want to identify the physical field. The physical field must have a positive mass square. And I have to know what the field is, and I've deduced that the field should be whatever tells me, whatever shows me, whatever measures the life around the ground state. In the past, v was 0 always, so in the end, phi was equal to h, so you never had to worry about that. But you always actually had it present. You were fortunate that v was 0.
And we just did that to break the symmetry, let's say.
No, I didn't do that to break the symmetry. No, I'm just identify field. The symmetry is broken when I write down the symmetry will be broken by the ground state. When I write down my potential in the parameter space, when I choose the sign here, minus v, that determines the fate of what happens.
What confused me is that when we're living in the ground state there, we cannot say maybe the other ground state.
Oh, you can take this ground state also. Notice that I get v squared. The physical quantities cannot depend on which ground state you picked up. That, of course, has to be true, and you will see, whenever we compute something physical, you will notice it will not depend whether you live in one or the other. You know, in the case of this case, there's going to be more vacuum, you can imagine. There's going to be, what will be the vacuum manifold, by the way? Tell me. Guess it. A circle, S1, right? Because now it's a complex field, it's going to be a circle, so you can now have an infinity of different vacuum physics, cannot depend which one of you picked up, okay? There will be an interesting consequence there, that it cannot depend. Whatever we compute should always be independent of which vacuum. So we could have called this, by the way, in other words, this is V Goran plus H Goran, and this is phi minus V Mahmoud plus H. You say, no, I want to live here. The physics should be independent of whether we took this or this. You can give me the same name here. You say, no, I want to live here. You'll find out that, of course, since there are two possibilities, you cannot define what is left and right. Only after somehow you break the symmetry you can define it, but not before.
Maybe my question is, what is the physical motivation to let's say, to look at, to both that we have two ground states which is identical, instead of only one ground state? Is it
What is the physical motivation for what? let's see.
To
If
don't have only one ground
I don't choose the number. There was no motivation for having ground states. Ground states were they were. You can't. No, the question. Okay, maybe let's try to see what you could be asking that we could be. You see, let's reflect. Let's step back. I need to show you what is the physical motivation. What am I doing? I want to break symmetry spontaneously. I'm in the situation in the early 60s. I break it by hand. I break it hard, as we say. I break it really the way Glesho does, and it doesn't work. Then you say, well, if it doesn't work, I have to learn some other way. It's not obvious that this will be a good way to do, but I want to find an alternative. Spontaneous symmetry breaking means I take a symmetric theory in which everything that I write down is symmetric to start with, but then the ground state decides to break the symmetry. Okay. If I have a symmetry, that means there will be more. Once I have a symmetry, there will be more than one vacuum. So it's not the number of vacua that I decided at the beginning. There must be. Look, because Kemi said immediately, if you have a circle symmetry, you're going to have a vacuum manifold which is a circle. You take that symmetry, you will have that. If your symmetry is a sphere, you will have a vacuum manifold which is a sphere, because that will correspond to the situation you started with. The fact, of course, so it's not the motivation, it's not, manifold is what it is. There is no motivation anymore, everything is fixed. I know I have to live in one of these vacua. What I know, that of course you cannot believe, and that's why, I would advise you, I will give you some examples that I would advise you check for yourself that physics does not depend on the vacuum you pick up. It's good to check it, even by brute force sometimes, although physically, obviously, it should not. So when I give more complicated example, it would be good for you to say, well, I don't believe quantum. Let me see. Doing a calculation sometimes gives an additional insight. You will convince yourself every time, as it should be, since I have a symmetric set of possibility. What doesn't matter which one I picked up. If the situation is symmetric, it doesn't matter whether I picked up this or this as a left or right.
What about the cubic term in the potential if we choose Picard and not Mahmoud?
Sorry?
The cubic term in the potential?
Yes.
If we choose between one or another?
Right.
That will have a minus or a plus.
They will have a minus sign. Obviously, it cannot be physical. So the sign will not be physical. You will calculate something, okay? You and I will decide what we will calculate, and we'll end up concluding the same thing. Oh no, there will be thing that depends on the sign, just like this. I'm saying whatever is the physical quantity, we'll have to, okay, we can come back to that. We'll do some scattering, and we'll see that it doesn't depend on the sign of E. Or the phase of E. It's sort of better to study this when we have a really complicated situation, and it's even not just the phase, it may be some group rearrangement, okay. It would be nice to know that any point is equivalent to any other point.
But we need to choose one to break the symmetry.
We have to choose one. Well, I'm tempted to say something, but I'm struggling not to say something. I'll postpone it. Anyway, it's late in the day, and I have actually assumed something tacitly. But if you don't notice, it doesn't matter. Maybe you will notice. I made an assumption.
But we don't tell everything.
Right.
Yeah, that's
Right. See how you don't ask. Notice that nobody. I've seen this year after year, and I didn't ask also. I remember when I was told this. What happens when you're in quantum mechanics, when you had a double well potential? There is no symmetry breaking, because you tunnel like crazy. You don't actually live in a single ground state. In one of these guys, the ground state is a symmetric combination. You can do a double well potential. You will find out that the ground state is symmetric. You live equally in both. And here is a non-trivial. I hate to talk about it because because I don't have a simple way of telling you that there is no tunneling in field theory. In other words, it takes an infinite time to tunnel from two degenerate, from one vacuum into a degenerate, another degenerate one. In field theory, you see, because of the whole space-time you live on, let me see, if it's bugging you, I may say something. There is a beautiful theory of vacuum tunneling developed by, it was studied before by Voloshin and Okun, but there was a series of papers by Coleman, and then later by Coleman-Kalan and Deluccia Coleman, who studied this issue. What Coleman shows, Coleman does this, he computes the vacuum tunneling from a local to a global, when actually to a lower energy, and then takes the limit when they are degenerate. It's beautiful and shows how this vanishes, okay? I don't have a simple way of telling you why this is, without saying something about tunneling itself. So I'm actually assuming a very important result, that in field theory, unlike in quantum mechanics, which is one-dimensional system, in an infinite-dimensional system, the tunneling between the degenerate vacuum vanishes. That was crucial. I'm glad that you have noticed that. There was a cheating. I cheated. Well, I didn't cheat, it's true. We have to live in a So the question that we face today in physics, it's very interesting, okay? Once people noticed that after this was developed, then you realized that normally you would think that you have to live in the global minimum. So imagine you have potential, it says in order that life be stable, I should live here. However, what matters is the time, since tunneling may be slow. So you can imagine, you remember how in quantum mechanics the tunneling depends on the distance, the probability? Right, there is an exponential dependence, WKB, you can think of that. It was the height, of course, mattered, but the distance between these 2 points. So if the points are distant enough, the time to tunnel may be longer than the age of the universe. You and I, not only that life is unstable in so many different ways, and we have to die and whatnot, and the universe itself seems that it's cooling off, okay. I'll comment from time to time, we should, it's sort of nice to have I don't want it just to be a monologue, to have a dialogue between Paolo and me, that you see that we can learn the field theory of the standard model to discuss some of the profound cosmological issues and vice versa, okay. There's a deep interplay between particle physics and cosmology, that's why some of you want to do it, okay. We'll try to emphasize this point, the astroparticle physics, because the universe was very hot in the past. And because it was very hot, it was warm in the form of elementary particles, okay. So it may be that actually you and I live in the unstable universe. We will not care if the lifetime is very long. It has to be bigger than about 10 to the 10 years. And it boils down to the thing that in the degenerate limit that you can actually, I can say a few words sometimes, okay, that's not part of the course. Anyway, we don't worry about the discrete symmetry, we are now going to go to other examples, okay. In this case, I assume no tunneling. Okay. The lecture is over, right? So let's turn this off.